magnetars are super interesting objects, and I hope this will be, you know, the message throughout the presentation, so that at the end, you would agree. So what we really want to know is about the physics of these objects. They are extreme. There's extreme phenomena going on in these objects, and something that we cannot test in the lab. But you know, start from the beginning. Magnetars are neutron stars, and neutron stars themselves, not only magnetars, but in general pulsars and all of the neutron stars that are known, are the smallest and densest observed object. So you imagine to have the sun and shrink it down to not only Earth, but the size of a town. And this is more or less the size of a neutron star, but you have the full mass of a sun within it. And the magnetars are a particular type of neutron stars because they have the most intense magnetic field in the universe. And just to give some numbers, because I always have impact on this, this is the magnetic field of Earth, very small in terms of units of Tesla, a sunspot at 0.4 Tesla, an MRI deals with magnetic field strength of 10 Tesla. A normal neutron star, we are, you know, way higher up in magnetic orders of magnitudes, is 100 million Tesla. But a magnetar is even 1,000 times stronger than that. So you can imagine the whole physics, comes in questions, and how is the physics behaving around these very strong magnetic fields. And one very interesting effect is the quantum birefringence. That is an effect expected when we're dealing with the strong magnetic fields. And birefringence is the optical property of a material that have a refractive index that depends on the polarization and the propagation direction of light. When this happens in void, magnetic fields can affect the void itself, changing their properties. And the result is that the light coming from the surface of this magnetar gets filtered out through this split void and comes out 100% polarized. And this was one of the major science cases for XP when it was launched. Turns out that we are not being able to test this. We are not able, and this energies to really disentangle the case of a geometric polarization due to patches, hot patches on the surface instead of quantum birefringence. So, you know, this is still, the proof of this is still an open question. But what we can learn about the physics involved in magnetars can really come from their transient activity. I will go through in the next slide the different types of transient activities that magnetars can show. And the message being that during these events, we can learn something more about the nature and the physics behind these objects. So in this table, I will fill it up, and you have on the duration of the type of transient activity and its peak luminosity. So starting with short bursts, these are actually one of the main activity that makes us realize there's a magnetar there. When these objects go and produce some bursts, they kind of light up, and in the gamma ray monitors, soft gamma rays, hard X-rays monitors, and we can pay attention to what happens there. And most of the times, this is the major channel or magnetar discoveries. So in terms of phenomenology, we can see how these bursts have really different light curves. These are, for example, some series of light curves from bursts from the same magnetars, SGR 1806, during the active period in 2003. And you can see events with 2 peaks, multiple peaks, one single peaks. And of course, the study of the phenomenology of these events can give us clues of the physics that produced them, and then what's the physics behind these objects. The real question that we want to answer is what actually generates these huge magnetic fields in the first place. The spectrum of this burst is typically a black body, so a thermal component and a non-thermal component, usually modeled as a power law. These timescales are very short, so we're talking about tens of seconds. And one other thing, interesting thing that you could do when you have this large amount of repeated bursts from the same object, you can look at the fluence distribution. And in this nice paper in 1995, the fluence distribution of energy distribution of the burst from SGR 1806 was compared to the energy distribution of earthquakes from different sites on Earth. And it was noted how these are fairly similar. The earthquake distribution, energy distribution on Earth follows the known Gutenberg-Richter power law. And it was interesting to see how this Magnetar burst activity was kind of reproducing the same behavior. And this pointed towards, the conclusion that magnetars have, like Earth, a solid crust. This is in general true for, believed to be true for neutron stars. So just to, again, because numbers have a high impact, this neutron star piece of crust of a neutron star is so dense that if you shrink it down to or pick like a sugar cube size amount of neutron star crust, on Earth it would weigh like an average mountain. So it's extremely solid crust, and you can imagine the strength that you have that has to be involved to break this star, make it crack and produce starquakes. All right, moving to a different type of transient activity, we have outbursts. So outbursts have a longer duration, weeks, months, even years. And usually the X-ray luminosity rises up to 1,000 times the quiescent level. I won't spend a lot of time on this type of transient activity. However, this is interesting, definitely for axis, as the phenomenology itself allows a very easy follow-up, and definitely this should be a science case that the community should follow up with axis. If nobody does, I can, trigger some observations. And the reason being, of course, it's a slower transient activity, and so allows follow-ups with pointing telescopes. But there's, of course, a lot of physics that you can explore in these types of phenomena. We observe changes in the pulse profile. We observe an increase in flux coupled with a decrease in pulse fraction, very interestingly. And there's an evolution in the spectrum as well. So all these can give us clues on the physics behind this phenomena. And to add to this, what is often observed during outbursts are burst storms. So if you're lucky enough that you're already on target observing an outburst from Magnetar, actually the interesting thing would be a monitoring campaign, because the duration could be very, very long. but you can be lucky and have a burst storm occurring while you are observing. And these are basically tens, hundreds of bursts happening in a time scale of minutes, tens of minutes. And then you could have and collect a lot of nice statistics of bursts to then study. For example, a very famous burst storm is the one that happened in 2020 by in a Magnetar SGR 1935. Well, this is famous for one particular reason. Here I just that I will tell in a second, but here I want to show what could be a typical burst storm. And this is a nicer observation. And in particular, the zooming shows a period of about 20 minutes in which 217 bursts were detected. Again, these are very short pulses, so requires a quick readout. One thing that you can do is studying, again, the burst fluence distribution. And what is interesting in this case, it's being sensitive enough to go to very low fluences where you are not limited anymore by your instrument. And if you observe something that deviates from the power law that you can extrapolate down, then that will give you clues on what's the limit of energetics that can produce these bursts. And this is another very interesting parameter that tells us something about the physics involved in this object. As I mentioned, this burst storm was famous because of the observation from CHIME of a fast radio burst at the same time. So in the NICER, unfortunately, NICER wasn't observing at the time of the FRB, but Integral was. And this is the plot from the paper by Integral team, in which you can clearly see the two pulses of the CHIME fast radio burst that with a delay coincide with the peaks in the gamma rays. It turns out that this specific burst during the storm that happened to be in coincidence with the FRB is a peculiar one, is a peculiar Magnetar burst. And you can see it from this study, Georgionis on the right, where it shows the distributions of parameters compared to the whole burst storm and the one for the event in coincidence with the FRB. The photon index is completely off, and also the energy cutoff that you model the spectrum with is off as well. So it was a peculiar burst, but it was also a peculiar FRB, but I won't cover that. It's basically way lower energetic than the cosmological ones. So there is a question if these FRBs are a different population, but the key question is the connection between magnetars and FRBs. So magnetars could explain at least a fraction of FRBs. All right, and then there's my favorite and last transient phenomena from magnetars. There are the giant flares. So these are characterized by a very bright pulse peak, milliseconds long, and then followed by a periodic tail decaying in time. The periodicity is given by the hotspot, the fireball that is trapped plasma nearby the surface of the magnetar that rotates with the star. This is what we're seeing, the modulation that we're seeing in these light curves. These are the three events that happened either in the Milky Way, so from galactic magnetars, or the very nearby Magellanic clouds. So these are the only three, we call it galactic events. And what happened there is that we couldn't really characterize very well the bright peak because it was blinding. It blinded all the monitors that were observing there. But then there's this clear signature of a periodicity and decaying tail that kind of gives the smoking gun signature that we're looking at the magnetar because of the rotation. And here are some details. One thing that I want to highlight, of course, studying the spike of magnetar giant flares is very interesting. It tells you something, about the energetics involved that are very high. But we could also maybe learn something looking at the tail, and some interesting fact that we could observe already from the three events that we have is that if you look at the isotropic energy in the slide and the second table, I don't see my cursor, so probably you can't see it either. But you can see how the order of magnitude is very similar, despite the fact that the isotropic energetic of the spike is quite different among the three events. So there are some questions there. So what are the magnetar giant flare tails standard candles? And of course, this could be very interesting. And other questions could relate to, because we observe the spike when it's collimated towards us. Can we observe orphan tails? Because maybe the spike was pointed off our line of sight. And of course, other questions that can help knowing something more about magnetar as a population is what is the intrinsic rate of magnetar giant flares? Because that, of course, constrains what are the progenitors of magnetars themselves, what produces magnetars, and other STEM questions. So one thing that turns out to be very, very interesting lately is the observation of extragalactic magnetar giant flare. And here the point is that we are now not saturated when we observe the high spike, a very intense spike, because it's farther away, but we lose the smoking gun signature of the tail. So far we have several different magnetar candidates from nearby galaxies, but nonetheless, this helped us increase the number of magnetar giant flares and constrain the rate. Okay, I can just quickly say here that this magnetar giant flare from the Sculptor galaxies was observed up to GeV energies. So this was the first time that we saw such a high emission from a magnetar in general. But then, as I said, you can constrain, you can look for magnetars in extragalactic, in other galaxies, looking for the magnetar giant flares. And here's a search led by Eric Burns, in which accounts for, because they would show up as GRBs, accounts for the probability distribution of the GRBs in the samples that are very well localized. And then account for when these occur in spatial coincidence with the magnetar, with the local galaxies, and of course, waiting for the star formation rate, as we expect that magnetars are formed where you have more star formation activity. So we expect the star formation rate to trace the number, the rate of magnetars giant flares. And with this study, basically a sample popped up at beyond 5 sigma significance, that we have a population, at least a fraction of GRBs being non-cosmological, but coming from magnetar or a different source. And because of the space alignment, only thing that could explain our magnetar giant flares. And so that search highlighted 4 additional events that are listed here. And on the bottom, there's the chance alignment. So it's a very, 1 in 7,000 and 10,000, 130,000. So it's a very small chance that these are coming from that region by chance and not our magnetars in that galaxy. And also you can observe that these extragalactic magnetar giant flare events or candidates look very similar in terms of energetic and duration as the galactic magnetar giant flares. And they look different from the population of short GRBs. So we kind of constrained that 2% of short GRBs may have a magnetar giant flare origin. Okay. This is interesting, as I said, to constrain the formation channel that magnetar, what produces magnetars. And the question again, it's what produces this huge magnetic fields. And we can have different formation channels. Core collapse supernova, collapsers and superluminous supernovae. You can have neutron star binary mergers that can produce magnetars temporarily that can collapse into a black hole then, or actually stabilize as a magnetar. But there's also this new formation, accretion in this collapse of a white dwarf that can produce magnetars as well. And knowing the rate of magnetar giant flare, how often that go off, how many of them can observe are in the local universe, we can tell what is the formation channel. You can have a low formation channel, like something that produces only a few magnetars if you have a lot of magnetar giant flares. And basically what we concluded is that so these are some numbers, the local rate that you see up there is quite high. And you can see it compared in the second column of the table to different types of events. So these local rates are huge, which is good news. We have a lot of these events, but we only have identified 7. So what's the deal there? So they are very hard to identify, but one other thing that we can constrain, as I said, is that the intrinsic rate at being so high favors the core collapse supernova. And one other thing that you can maybe constrain at this point is what is the rate of magnetar giant flares per magnetar? So far, we have seen only one magnetar giant flares per magnetar, but we know that these are not disrupting events. So do these repeat? And this would be interesting on its own because as these are a source of short GRBs, this will be the first repeating source of GRBs. But going back to the question, why we only observe 7, it's basically due to the spectrum being hard. And the fact that our monitors in the soft gamma rays, hard X-rays, we have what triggers them is the number of counts. And if you have a harder spectrum, you have fewer counts in that trigger band. So a higher energy or a wider band triggering window could help with this. And for example, maybe COSI can help detecting more as a monitor. But we also calculated that there should be, in fact, more in the sample. And I'll go quickly over this because we have a student that actually looked into all the archival bursts on the GBM and searched for additional events that we expect to be there, and found the 13 candidates. Only one interesting in the sense that was 3 sigma, beyond 3 sigma level. And this, interestingly, was an event from the same Sculptor galaxy. This is how the light curve looked like and compared to the previous magnetar giant flare Sculptor galaxy and neutron star merger events. And And these are the luminosity distributions of compare the neutron star mergers and the Magnetar candidates. And they're clearly different, and you can kind of understand how the phenomenology of the events are different, and quite confident that this was in fact a Magnetar giant flare. I would skip on this part, even though it's interesting, but it's all in the paper that is out. One interesting calculation you could do: what is the chance that you get two Magnetar giant flares at a distance of a few years from the same galaxy, and what's the probability that these two events are uncorrelated? And of course, this is to see if we could answer the question, is this from the same Magnetar? And of course, we couldn't answer this question but yet with these statistics. And there's a 9.9% chance probability that events are uncorrelated and 90% confidence. That was an interesting exercise. There was a recent Magnetar giant flare from M82. But one thing that I want to go to conclude is that we expect, there's this paper in preparation led by Paz Benyamini that wants to give some tool to the community and in particular instrument developers to then, like a figure of merit and understand what are the performance of an instrument given the population of Magnetar giant flares. So in this case, you can see from the plot on the right that there's the number of Magnetar giant flares compared to short FRBs, but as a function of fluence. So the fainter Magnetar giant flares, of course, are more numerous. But the point here that you could use this study to understand how many Magnetar giant flare you would expect to observe in 1 year. And this is integrated over the whole volume. Okay, so if you take into account the axis field of view, I hope I quoted the right number, as around 10 to the -8 radiant. And we are in the fluence of 10 to the -10, we are about a 10 to the 8 per year, events per year. So this would mean that you could expect maybe one event by chance in the field of view down to this fluence of Magnetar giant flares in axis. But there's a caveat, of course. So these events are super short. So 1/10 of a second, and you need to have the readout capability to see them. And the spectra of these are quite hard. So this might disfavor soft X-rays, but it's still interesting to look at. One, I think, more interesting topic for axis would be looking into the Magnetar giant flare tails. So this would require to look farther away. Of course, you allow to have more volume and to observe more of these events to have the chance of observing more. And this is, for example, the number of counts given an effective area that you would expect integrating over the time after a certain repointing. So after the trigger time t0, and then minus the time you get on target, and what is the remaining counts that you can accumulate. So this for Swift XRT, and this is a far away object, 3.5 megaparsecs. But it's interesting to see how either you have a harder, like either you compensate, the fact that you're observing in a soft X-ray band with a high effective area, or you can have a hard X-ray coverage. But in both cases, this can enhance the number of counts, and you can have some interesting statistics to work with and study these events. And I think I can close here. This is just a plot of saying how interesting Magnetar have been over the years, and how this is still increasing. So I stop here.
Great. Yeah, sorry about that. I think it's actually on my end, maybe my internet was unstable. Yeah, that was a really nice talk. I think we have time for maybe one question and then we should switch talks. So, Richard.
Yeah,
Yeah, nice talk. On
thank
the
you.
giant, on the burst that was the same, we think, as the chime event, is the chime distance within our galaxy?
Yes, indeed. It's pretty clear that it's from that SGR that we know the distance of.
Okay, and one other quick one for the giant flares, since we don't know the spectrum of the ones we've seen here, the 3 events, how do we really know those spikes that are identified as magnetars really are? What is the physical evidence that says they're magnetars or
Right.
giant bursts?
Okay. Yeah. Well, for the galactic ones, there are some very small instruments that did not saturate. So that can give some clues. And there was a very interesting measurement done for, I think, the 2004 event, that a Russian satellite saw the event, not directly because it was behind Earth, but it saw it reflected off the moon. So it could reconstruct that energetic that way. But yes, like, there are some uncertainties, but for the ones that we have that measurement, it seems like that's, they're in line with what we see, that we can well constrain from the extragalactic bubble.
And they're not the band spectrum.
Oh, well, we still assume a band spectrum to fit those energies. But you can, have different assumption, and it's a typically harder spectrum.
Okay, thank you very much.
Yeah.
Okay, great.